This question is about one-tailed test versus two-tailed test. Say you have a sample of 100 observations, so n equals to 100. The sample size is 100, and you get the standard deviation and the sample mean. And the first question has null hypothesis mu equals to 90 and alternate hypothesis mu greater than 90. Now, because the alternative hypothesis mu greater than 90, if the alternative hypothesis is an inequality like this, then you know that it's a one-tailed test. As opposed to the other case where you have, for example, mu not equals to 90. In this case, it will be the two-tailed test. Okay, and that's the most important thing that you should know. That this is a one-tailed test, and we have to answer these three questions. Let's do one by one. So first, the test statistics is the z-score, and you calculate the z-score by this formula here. X bar is always the sample mean, mu is always the population mean, sigma is the standard deviation of the population, but if your sample size is 30 or greater, you can rewrite this as the sample standard deviation if there's no population standard deviation. And then n is the sample size. In our case, the sample size is 100, so we have to divide by square root of 100. I plug in the other numbers and we get the 1.9349. Okay, so for this test statistic, you have to calculate the p-value, but the p-value depends on whether it's a one-tailed test or two-tailed test. So let's think about what it means in this one-tailed test. You're trying to see whether this 94.4 sample mean is significant enough to denounce the null hypothesis mu equals to 90, right? So you want to see if 94.4 is too big. And in other words, what you want to see is that whether 94.4 and above gives you a significance level that's bigger than 0.05 or not. If it's less than 0.05, that's significant enough that you can reject the null hypothesis. If it's less than 0.05, then it's not as significant. If it's more than, if p-value is more than 0.05, then it's not as significant, and you don't get to reject the null hypothesis. So that's the thing. And once you use the z-score, it converts to the standard normal distribution, and you have to figure out the p-value as the area on the right side of 1.93. That's because we're using the alternative hypothesis that average is greater than 90, so you go to the right side of this value. If it was less than, then you would go to the left side. If the alternative hypothesis is less than, it would be to the left side. Okay. All right. So how do you calculate this? Well, one thing you can do is to find the area from 1.93 up till infinity, but often it's better to make the lower part as a negative infinity because your calculator has it in that form. So if you go to the calculator, to find the area for a given value, to find the p-value from a given value, you have to use the normal CDF, and you can see that negative 1e99, that's like practically negative infinity, which is negative infinity, and it's really hard to put this back in if you change this to other numbers. So it's just a good idea to just leave this as lower as untouched, but then put that 1.93 on the upper and paste that, and you get 0.97319, but that's the area before 1.93 because in this format it's always from negative infinity to that number. Therefore, the p-value has to be computed as 1 minus this value. So if you do 1 minus of the second vars, go to the normal CDF, put that, then you get this 0.02680 as your p-value. Okay, so that's your p-value. And then, as I said before, since this p-value is less than the significance value, then it shows you that this is significant enough, meaning that the probability that such a high number would happen under this null hypothesis is less than 5%. So it's not very probable that null hypothesis would be true. So you take the alternative hypothesis, mu greater than 90, and that's your conclusion for this test. We're rejecting H0 because the p-value is less than the alpha value, which is the significant value, and we adopt H1. Now, on the other hand, if you go to the two-tailed test, the test statistic is still the same because nothing else changed. But then when you take the p-value, p-value would have to be two-tailed because here's how you think. The rejection region with 0.05 significant value is that since it's two-tailed, you have to take half of this and you have to find the point where beyond it is 0.025 because that's the half of 0.05, right? So you have some value here where afterwards it will be 0.025 and there will be another one with 0.025. And actually this is one of those places where it's used widely enough that you should memorize. It's like 1.96 and negative 1.96. So if your rejection region is, if your test statistic is in the rejection region, meaning that it's bigger than 1.96 or less than negative 1.96, then you can reject the null hypothesis and choose the alternative hypothesis H1. But as you can see, this is 1.93, so it will be less than 1.96, right? So the conclusion is that we cannot reject H1. That's the conclusion. But it's asking for the p-value as well, and because this is a two-tailed test, what you have to do is not only you take account of this area, but you also take account of this area as well. So you have to double it, being a two-tailed. So the result is that you have to double it, and 0.0536 will be the p-value, and the conclusion is that we cannot reject H0. Note that saying that we cannot reject H0 is different from saying that we should adopt H0 to be correct. If you say H0 is correct, that's not a good conclusion because we don't have evidence for it. But what I'm saying is that there is no evidence against H0. That's all we know, okay? With the significance level of 5%.